recent years, scientists have witnessed many impressive discoveries in the field of quantum physics. Researchers continuously seek and decode the deepest mysteries of the universe, aiming to expand our understanding of the fundamental principles governing everything in the universe. In a recent study, a group of physicists, including Associate Professor Tigran Sadrakian of the University of Massachusetts, discovered a new state of matter called Bose-Cairo liquid state. Matter states in the quantum world often have much stranger and more complex properties compared to the states we encounter in the everyday macroscopic world. Bose-Cairo liquid state is a special form of quantum state, appearing in interacting boson systems, particles that follow Bose-Einstein statistics under certain conditions. Bose-Einstein statistics describe quantum systems where there is no limit to the number of particles distributed at the same energy. This state has liquid properties and is Cairo in nature, meaning it breaks time reversal symmetry and has handedness symmetry. This discovery opens new directions in humanity's efforts to understand the nature of the material. Bosons are particles that can occupy the same quantum state. However, in the Bose-Cairo liquid state, bosons do not condense into a single quantum state but form a more complex state with liquid-like properties and distinctive characteristics. Cairo and time reversal symmetry refer to the property of a system that can distinguish between left and right, similar to two hands being mirror images but cannot be superimposed. A Bose-Cairo liquid state breaks time reversal symmetry, meaning its behavior is not symmetric when the direction of time is reversed. Under normal conditions, matter can exist in solid, liquid, or gas states, but when entering the microscopic world, at temperatures near absolute zero, with objects smaller than atoms, or at extremely low energy states, everything becomes very different. Sadrakian says, you will find quantum matter states in these regions, and they are much more complex than the three classical states in everyday life. Sadrakian has spent many years exploring these special quantum states. In particular, he has focused on phenomena that physicists call Samide générosité, moire, or kinetic failure. Normally, particles in a system collide with each other and cause predictable effects, similar to billiard balls colliding, then moving in predictable patterns. In other words, the effects in particles are correlated with each other. But in a quantum system with kinetic failure, there are countless possibilities arising from particle interactions. Perhaps the billiard ball would fly up or bounce out at unusual angles, and some of these countless possibilities could lead to novel quantum states. For example, Bose-Einstein condensate, which is a collection of atoms cooled to temperatures just above absolute zero. There, most particles in the system will fall into the same ground quantum state, forming a shared quantum state. In addition, there also exists a phase of matter simply called time crystal. This is a special organization of matter where particles not only arrange in periodic structures but also have periodicity in time, even at the lowest energy state. Sadrakian and colleagues designed a first Chasen machine. This is a two-layer semiconductor device, the top layer containing electrons that can move freely, the bottom layer filled with holes, positions that an electron could occupy. Then, these two layers are brought very close together, closer than the distance between atoms. If the number of electrons in the top layer and holes in the bottom layer are equal, you will see particles acting correlated. But Sadrakian and colleagues designed the bottom layer to have a local imbalance between electron and hole numbers. According to Sadrakian, it's like a seat-swapping game designed to make electrons in first Chasen active. Instead of each electron having a fixed seat, they now compete to secure many possible positions. This first Chasen phenomenon triggers the novel Cairo edge state with astonishing characteristics. For example, if you cool quantum matter in the Cairo state down to absolute zero temperature, the electrons freeze in a predictable pattern. And the electrically neutral particles that appear in this state spin either clockwise or counterclockwise. Even if you collide another particle into one of these electrons or apply a magnetic field, you cannot change its spin. What's even more surprising is what happens when an external particle collides with a particle in the Cairo edge state. Returning to the BR ball analogy, you would expect the number 8 ball to fly away when hit by the cue ball. But if the BR balls were in the Bose-Cairo state, all 15 balls would react identically when the number 8 ball is struck. This effect is due to the widespread quantum entanglement in the system. For a long time, the Bose-Cairo state was rarely mentioned due to difficulties in observing it. To achieve this, the team of scientists from Nanjing University and Peking University designed a theory and experiment using it capable of measuring the movement of electrons as they move to find seats. According to the scientists, at the edge of the two-layer semiconductor, electrons and holes move with the same velocity. This leads to spiral transport, which can be further adjusted by an external magnetic field as the electron and hole channels separate under stronger magnetic fields. Consequently, magnetic transport experiments successfully revealed the first evidence of Bose-Cairo liquid. So, what exactly do all these new forms of matter bring us? Further exploration of this state will help uncover new answers and other mysteries in quantum mechanics. Specifically, systems in the solid state, such as Bose-Einstein condensates in Cairo solid state, a special form of in it, the solid state not only has solid properties but also breaks time symmetry and exhibits Cairo. This new state could provide a shortcut, changing how we process and transmit information in quantum computers and quantum technology-based electronics. Implementing Bose-Cairo liquid states can be challenging and often requires precise control of boson system interactions and cold atomic gases in optical lattices and some two-dimensional materials under specific conditions, like strong electric fields or spin-orbit coupling, or potential platforms for observing these. Thank you for watching this fascinating video.